Hello calculus class, this is a homework question from your 311 homework. This is the very last problem, number 15. And if you were to do this problem and click on view an exam, it would have you do all this work to find, oops, right there, all these little parts over here in this part, where the angle is. And if you're going to do it all by hand, that is necessary, but with your calculator you have a lot that you can do that'll help you find this angle without having to do all that extra work. And I'll show you how to do that in just a second, but just know that you can do this problem and stay kind of within this triangle and then use technology to help you get into this triangle that's needed to find this angle. So anyway, I'm going to show you how to go about doing that with staying within this triangle. So the thing you need to understand here, the big important thing, is that one of these boats is heading due east. That's this one. The other one is heading northeast. Okay, and by northeast we mean perfectly northeast. We're not giving a bearing like north 20 degrees east or something like that. If it's northeast, then the assumption here is that this is a 45-degree angle off of that boat that's headed due east. Alright, and because that's a 45-degree angle, and we're this one's due east, this is straight north right here, so this is a 90-degree angle, and since this is theta, this is 90 minus theta. Okay, so 90-degree angle, this is theta, this is 90 minus theta, and then if you work it out, this angle up here, because the three angles in a triangle have to add up to 180, this angle up here has to be 180 minus this, which is 135, minus this, which you have to distribute, so 135 minus 90 is 45, and then minus and minus is a plus theta. So this angle up here is 45 plus theta. Alright, and then it says in the problem to call this x and to call this z. And because we have something to write for all three side lengths, we can set up the law of sines here for x and z. So remember, when the angle is not 90, the angles that you're dealing with in your triangle, it's not a right triangle, then typically you use law of sines and or law of cosines to solve those things. So we have the angle measures, we have two of the side lengths. We can set up the very first thing that we have to do for this problem is set up an equation that relates x, z, and theta as the first part of this question. So what we end up with is a law of sines. We can say that x is to, this is side x. The angle opposite that is over here. So x is to the sine of 45 plus theta, as z is to the sine of this, sine of 90 minus theta. And then if we cross multiply, we end up with x sine 90 minus theta equals, cross multiply here, you get z sine 45 plus theta. Alright, now at this point, there's a couple of trig identities you need to know. The first is the cosine is, if you remember that this is just a shifting of the sine function, and we're shifting the sine function over 90 degrees or pi over 2 radians. So if you think about that, that's the same thing as the cosine function. That's, remember what cofunctions are. The trig function, cotangent, cosecant, is just the original function, and it's, the angle is the complement of that other function. So what I mean by that is, if you remember, I'm in degree mode, so make sure you're in your degree mode. If I take the sine of 10 degrees, alright, the cosine of 90 minus that, or the complement, which is 80, two angle measures have to add up to the same thing, will be the exact same output. And it works with the cotangent and the cosecant and the secant too. But if you take the sine of any value, 89 degrees, and then I take the cosine of 1 degree, alright, 89 and 1 add to 90, I'll get the same thing. So that's a property of cofunctions, co-trig functions. So the sine of 90 minus theta is just the cosine of theta. So I'm replacing that in there, and then on the other side I do need another trig identity. So this is a sum inside a sine, so we need the sum formula for the sine function, which if you recall is sine of alpha plus beta is the sine of alpha cosine beta plus cosine alpha sine beta. If this were a minus, the only thing that would change is that'd be a minus. So the sum and difference formula for the sine is this. So we're going to use 45 for alpha and theta for beta. So right here I've got sine 45 times the cosine of alpha, which is cosine of theta, plus now the cosine of the first one, cosine 45 times the sine of theta, using that identity. Alright, and now the next thing we're going to do is just evaluate this. Sine of 45 is the square root of 2 over 2. Cosine of 45 is as well. So we end up with x cosine theta equals z times this plus times the cosine plus this times the sine. This thing right here I'm going to factor out since it's common. I'm going to factor it out and put it with the z. And now I got x cosine theta equals z times the square root of 2 over 2. Alright, just factoring this common term out. And then I'm just left with cosine theta plus sine theta in the bracket. So cosine theta plus sine theta. Alright, and then the last step, I'm going to isolate x by itself. So x, divide both sides by the cosine here. Okay, so over here I got this sum. I'm going to have to divide both terms in this sum by the cosine. And so x is on the left side. This ends up being a 1, and this ends up being the tangent. So we're going to end up with x being equal to z square root of 2 over 2 times 1 plus the tangent. Right, and there's our answer to the very first part. So this is a relationship between x and z and theta. Okay, we've got them all related. Now, the first question that we actually have, this is actually the first part you have to do for your homework, but the first question we actually have is, what's the rate of change of the angle, right, d theta dt, 30 minutes after? So in 30 minutes, z will be half of this. This is miles per 1 hour, so 30 minutes is half of that. So this will be 15. And in a half an hour, this will be 12. So we know what z and x are half the time into their trip. So when we take this derivative with respect to time to get that d theta dt that we need, we're going to need to eventually figure out what theta is to be able to plug in and solve for this. You'll see that when we take this derivative, there's going to be theta is going to be a part of the equation for d theta dt. So let's just go ahead and do that. Let's take the derivative of this with respect to time. So over here to the side, I've got dx dt, alright, just taking the derivative of the left side with respect to time, equals, now on this side I got multiplication, so I'm going to have to use a product rule. So this right here is a constant times z, so if I use it as the first thing I take the derivative of, I'm just going to get the square root of 2 over 2 dc dt. Alright, so I'm taking the derivative of something just being multiplied, a function being multiplied by a constant. It's just the constant times the derivative. Right now I don't change the original, the other original, so 1 plus tangent theta. So theta is a part of the derivative that we're getting. And then I leave this alone, so z square root of 2 over 2. And now I multiply by the derivative of this. So the derivative of 1 plus anything, this goes away to 0. And then the derivative of tangent theta is secant squared theta. Alright, and then we chain on the derivative of that, so d theta dt. So there's the thing that we want to isolate, the d theta dt. So the first thing I'm going to do to isolate d theta dt is to move this to the other side. It's being added to this term of d theta dt, so all this gets subtracted over with the dx dt. Okay, now I need to divide this away. The way I'm going to do that is this is a fraction, so I'll multiply that by that reciprocal. But if you recall, the square root of 2 over 2 is the same thing as 1 over the square root of 2. It's just been rationalized. The denominator's been rationalized in this form. So if I'm going to multiply both sides by the reciprocal, what I actually end up doing is just multiplying both sides by the square root of 1 over the square root of 2, which the reciprocal is the square root of 2. So I'm just going to multiply both sides by the square root of 2. Well, I'm multiplying this side by the 2 square root of 2 to get the 2 to cancel. But I'm also, on this side, you'll see just a square root of 2 show up because I'm literally they're the same thing. So I can multiply either form. Like here, I'm going to multiply by the reciprocal of this as well because I want these things to go away. But over here, I'm going to end up multiplying by the reciprocal of this form just because it's just a nicer, cleaner thing. It doesn't have a fraction look anymore. So when I clear out fractions on the left and right, or when I multiply by this reciprocal, I'm going to multiply by square root of 2 over z here. So I end up with the square root of 2 over z dx dt. Alright, and then here, these cancel. I end up with just a 1 over z, and then dz dt, and then 1 plus tangent theta. Alright, equals, this is gone now. I've multiplied both sides by this reciprocal. Alright, so it's now over here. Alright, and that equals secant squared theta d theta dt. Now, same thing. I want to get rid of this. I could divide both sides by the secant squared, but instead, the easy thing to do here is use the reciprocal properties of these trig functions and multiply by the cosine squared theta, right? Which is the reciprocal of secant squared, so they cancel. And then over here, I'm going to multiply by cosine squared theta. Alright, so I got square root of 2 over z times cosine squared theta dx dt minus cosine squared theta over z dz dt times 1 plus tangent theta. Alright, that equals d theta dt. Alright, so now we're ready. We've got something for d theta dt. We're ready to plug in these values from the original that we know. The problem here is, and the reason why help me solve this as you do all that stuff over in this triangle is to be able to have an expression to give you theta. Well, we're going to use this equation right here to give us theta, and well, really we're going to substitute cosine in there. So it's going to be that with cosine is what's going to give us theta. We're going to be able to solve for x and z. Okay, we'll be able to solve for x and z because of their property and how long they've been riding. We've got them right now for this first part. So we can plug x and z in there, and then we can use our calculator to help us solve for theta, to tell us what theta is. Alright, so let's take this previous equation that we have here and plug in the stuff we know. We know what theta is. We know what z is. Alright, z is 15, so we're going to plug in a 15 where those z's were. There's 15 right there as well. Alright, dx dt, that's how fast the boat that's moving due east is moving, so that's 24. So we'll replace 24 where the dx dt was. Alright, and then dz dt, that's how fast this thing's moving, which is 30. Alright, now let's clean this up a little bit. There's a cosine squared. Let me just change that to 2. And then this can be written as 3, 5, and 8. Okay, so we got cosine squared. I'll pull that out, and then I'm left with just 8 square root of 2 over 5 minus this guy, 2 plus tangent. Okay, now everything that's remaining in this thing that's unknown has to do with theta. All right, it has to do with the value of theta. So what we're going to do is we're going to go back up to this guy right here, and again this is with cosine. I'm going to go ahead and just erase it so you'll have that. This is going to be cosine in our formula that we're going to use. We know x now. X is 12 for this scenario. We know z is 15 for this scenario. What we're going to do is use our calculator and plug in and figure out what the angle has to be. So in my y1 I've got 12 cosine theta. Alright, well, x. I've just replaced the variable that's unknown with x. And then in y2 I've got 15 sine 45 plus x. Alright, and if I graph those, my window is this, by the way, 0 to 30 degrees. 10 as the scale, and then 0 to 15 for y, and scale 5 there. If I graph those, there is the 12 cosine theta, and then here comes the z sine 45 degrees plus theta. So right there is where they hit. That's what we're looking for. We're looking for where they hit, what value of theta makes these things intersect. Then I just go down here to intersect, enter, and then you can just hit enter again, but just to get close for the guess. And then once it computes it, this value for x that we have right here, that's stored as x. If I hit mode, if I hit second mode and quit, and I just hit x, that's stored as x, right? The angle. Now, just to make it less confusing, because we already got an x, I'm going to hit STO, that's store. And then if you look here above the 3 key, there's a theta. I'm going to press alpha 3, the green theta, and I'm going to store that number as theta. Okay, and now I'm ready to do the last part. d theta dt, I'm going to plug this expression into the calculator, and now everywhere I hit theta, the calculator is going to put that number right there in for it, that angle. Alright, when you're time to call this variable, the theta, you just press alpha 3 just like we did before. So that's the cosine squared theta. Just typing in the rest of this expression, so the 8 square root of 2 over 5 minus 2 times 1 plus tangent theta. In the parentheses, there's the parentheses that is acting as the bracket, and there's the parentheses that's acting as the right bracket. So I hit enter, and it tells me that's 0. You may be thinking, well, what? That doesn't make sense, but let's look and see if it's this one. Cosine of theta squared, is that what's causing it to be 0? No. So it has to be that this is what's causing it to be 0. And if you look, the thing that we're subtracting from 8 times the square root of 2 over 5 is 2 times 1 plus the tangent theta, which is that number. Well, 8 times the square root of 2 over 5 is also that number. So this is 8 times the square root of 2 over 5. So when we subtract those, we get 0. So that means that the angle is not changing at that time. So the speed that this one's going, even though this one's going a little bit faster, the speed this one's going, with that angle being what it is, moving it back a little bit due to the fact that this one's not moving parallel to it. This one's going fast enough to where that angle doesn't need to change. They're always staying on that same angle back towards one another, or at this moment in time they are. Now if we do the next part says, what about 3 hours after the boat leaves? Well, the only thing that's going to change in your work at all here is your values for x and z. So instead of them being 15 and 12, now it's been going for 3 hours, so this is 90, and this is 24 times 3 is 72. Alright, and if you go back into your equation, or your calculator, y equals, this will be a 72, and then this will be a 90. Alright, and then when you solve for the angle, you'll have to change your window, since 90 and 72 are being multiplied by sine and cosine. Notice before we had our y max at 15. That was because before the biggest of these two numbers was 15. Now the biggest of these two numbers is 90. So we'll switch it to 90, and I'll switch that to 10. And then when I graph this, here's the 72 cosine theta, here's the 90 sine 45 plus theta, and if we find their intersection, what's their intersection? Look at the number we get. And if we go back and look at x, that's what we just got from our thing, and we look at theta, it still hasn't changed. So when we go through the rest of this stuff, yeah, all these in this formula down here, when we plugged in the values for z and the values for dx dt, dz dt, the z is going to change. It's no longer 15 like it was. Now it's 90. So we end up with this equation down here because of the values of z have changed. But now if you think about it, how many 24 and 90 have a factor in common? So I take 24 divided by 90 and reduce that fraction. I get 4/15. And then 30 over 9 is 1/3. How much bigger is 1/3 than 4/15? Is 1.25. Well, how much bigger is 2 than 8/5, the number that's in front of that square root of 2? 2 divided by parentheses 8/5 is also 1.25. So what I'm trying to get at is, no matter what, whatever these three values are right here that come together to be this first thing in this bracket are always going to be equal to these three things right here that come together to be the second thing in this bracket. Okay, the fraction here that this reduces to times the square root of 2, and the fraction here that this is the speed of one of the boats, this is the speed of the other boat, this is how far that boat moving northeast has gone. That fraction times the square root of 2 will equal this fraction times 1 plus the tangent of theta. It's always going to be that angle. Right? That angle is going to end up being constant because of the rate the boats are moving. Keeps it that way. Alright, so anyway, that's what you're going to get for both of these. You're going to get 0 for d theta dt in both parts of this problem, because this piece right here is always equal to 0 for that particular value of theta that we keep getting. And that value of theta that we keep getting is what is making this equation true in our problem, and it's always that same value. Okay, these heights may be going up and up and up and up because these boats keep traveling further distances, but where they cross, where they intersect here, is always going to be the same, and that value is keeping this ratio here, this number and this number, it's always keeping it in balance to where these things subtract away completely and always give you 0.